Hello, welcome to your own channel Paper Money. I am Biplab Datta and I am teaching you quantum mechanics for IITJAM, GATE and CSIR-NET, and it also covers most of the physics entrance exams at MSc and PhD levels. So let's start today's class. This is lecture number 26. All right, so we have been discussing the step potential, and we'll apply our knowledge what we have built and that thing to this the present problem, which is the 1D rectangular barrier. All right. So we'll start with the 1D rectangular barrier. Now, in this case, the potential looks like this, where the potential has a form which is given by let's draw it first and then talk about it. Okay, so this is x-axis, the direction, the dimension along which the particle is moving, and this is v naught, okay, the height of the barrier, and this is the vx axis, and this point is x equal to 0, and this is x equal to a. Okay, so the width of the barrier is a in this case. All right. Now, how does the particle behave when we have a finite, the width of the barrier is finite instead of in the case of step potential, which we had the barrier was infinite, the width was infinite. Okay. So that was a toy problem. It rarely happens that the potentials are infinite. Actually, the potentials are finite in like in practical, the experiments which we do. So this is where the observations are made. Actually, we're using this like a finite potential, like a barrier with finite potential width. All right, and from this we can associate this model with most of the like the quantum tunneling happening. Okay, in which is observed in like nature as well as in experiments. All right. So let's talk about it mathematically now. How do you define this? This is Vx is equal to, this is 0, P naught 0. Now this 0 in region this side, which is x less than 0, and here it is within this width, which is 0 between 0 and a, and this one is at x for x greater than a. So there are three regions. Okay, so this is region 1, this is region 2, and this is region 3. So we'll call it this way. So this is 1. Okay, so this is 1, this is 2, and this is 3. Okay, so these are the regions which we have separated the potential, the space into, not the space, the potential part. Okay, and the space part is here. The particle is moving along this. This is the dimension of the part, the space of the particle. Okay, it's not floating anywhere else. It's moving along this axis. Okay, the particle. Now I cannot draw a particle because it would make no sense. But just for illustration, we can show it here. All right. So what happens here is this particle, this one, we have already discussed in in unbound state and bound state lecture, what is the requirement for the particle to have unbound and bound states. All right. So for this case, there won't be any bound states possible. All right. This rectangular barrier, this rectangular barrier is repulsive is repulsive in nature. It's repulsive in nature. All right. And it's too cold to write. So repulsive nature, and hence does cannot support any bound state. All right. Now, in this case, how does the let's talk about it. If there's a case now, let's talk about the cases. What are the cases possible here? Now, as what we had done exactly, we'll do the same thing in step the, and this is the way we carried out the analysis in step potential. We'll do the same thing here also. So we won't be solving the Schrodinger equation from scratch as we did in step potential. We'll just take the results from there and put it here. All right, according to whatever situation is in the given region. So in this case, we'll take E greater than V naught. All right. So this is the first case where the particle is able to move freely in the whole region. Okay, and all values of x. And let's see how does things look here. Okay, so let's draw the diagram. Okay, and then conclude things from here. Okay, so this is Vx. All right, and this is the potential height. Now, in this case, let's say the energy is at this level. Okay, the energy is at this level. Okay, the energy is at this level. Now, this one is so how many of you are finding it difficult to wake up so early? Or is it okay?
It is okay, sir.
Yeah, but half of you are missing today. So I think it's a problem. So in this case, you have E. Now the total energy here is this one. The particle energy is this. Now what happens is, if, in this case also, the kinetic energy becomes the original one. Okay, there's the potential here is 0. All right. Now the potential energy is here is 0. All right, and yeah, I wanted to talk about like what subjects to focus on during the exams. If you have time, you should focus on all the exams. Okay, all the subjects. But if you have short on time and you have not studied the other subjects, but major topics you should always cover. There is no excuse for that. Okay, so uh, yeah, and quantum mechanics is one of them. Okay, so this is the kinetic energy in this region. Now, this one is region 1, this one is region 2, okay, and this one is region 3. All right, now what is happening here is, now is somebody raising hand? What happened? Somebody, okay, it was a mistake, I guess. All right, so what is this is, you have this mm, configuration, like this is the whole thing of the energy distribution for the particle with energy greater than V naught. And what can we say about the, let's just directly write it here. Okay, we don't need to solve it now. This part in this region, the region 1, there will be an incident wave, okay, which is, we are just writing the space part. We are okay, because when we talk about incident wave moving forward or backward, like we have the time part also, but we already know that all of them have the same time uh, like part. All right, so I will skip that thing. So this is the incident wave. All right, e to the power I kx. So this is moving forward. Now this is the solution which we had earlier. Now there's another component which will be moving this way, which is b iota, sorry, minus will be there. So minus iota kx. All right, so this part is clear as we had in earlier case. Now in this part, what will happen is, we have, what will be the equation here? Let's take f. Okay, let's take f, which is e to power I kx. All right, now there won't be any reflection part in this case. We know why, because the potential here becomes constant, which is 0. Okay, there's no change of potential here, neither it's going down nor it's going up. So there won't be any reflection component, and we know the beam is being sent from left to right, not from right. No, nothing is being sent from right to left. So we'll have one component here, the same argument which we had earlier. Okay, but in this, that in step potential, we had the width of the the well, sorry, not the well, the barrier was infinite. Okay, so in this case it's finite. So this region will be same as in case we have to take, we have to, this is Vx, in this case Vx is 0. All right, Vx is 0, in this case also Vx is 0. So this is the wave function we have in this case. And this within the barrier we have, now in this case, now it's not within, it will cross the barrier. So in this case we'll have, now there is a change of the potential, there's a forward moving wave, and there will be a backward moving wave also, because there's a change in potential, so there will be reflections also. All right, so we'll have one component here, which is, let me write it in some other color. So this, there is a reflected wave also. Okay, and this will have this equation. This will have, say, d e to power minus I k1x. So I hope this is very much clear. We are not solving any Schrodinger equation. We're just writing it using the results which we have obtained in step potential. All right, great. Now these are the components which we have in the wave function. All right, and let's see what happens. Let's talk about the momentum of the particle in each region. Okay, so region 1. Now this again is not it's not a real potential. The potential will have, of course, have some like it won't be sharp as this, as sharp as this. It will be maybe a gradual slope like thing or something like that. Okay, this is just a toy problem which we are dealing with. Okay, we start in physics, we always start with toy problems and then slowly build up. We keep on adding features and parameters and approximations to get the real, get close to the real thing. All right, um, all right, so this is the toy problem which we are talking about. Now the momentum of the particle, momentum of particle in region 1. Okay, so region 1 we are talking about is the momentum of the particle in this case, say p I equal to, this is h cross k. Okay, so k here is defined as this is 2m e by h cut square. All right, and so like we can get the de Broglie wavelength, which is lambda 1 uh, lambda I h by pi. All right, so this is the momentum and this is the wavelength of the de Broglie wavelength, wavelength of the de Broglie wave in this region. Now the region 2 and region 3. So region 2, we have P2 is equal to H cross K1. Okay, and in this case K1 is given by 2ME. Now in this case it's E minus V naught, all right, divided by H cut square. Okay, now the lambda here is lambda 2 not is H by P2. Okay, I've been telling you this is I, this is not I. Okay, this is 1, but it's in Roman it looks like I. All right, so this is P2, and then what we have is region 3. Now P3 H cross K is K H cross square. Okay, this is the same as the previous region, sorry, region 1. Now what is happening here is you can see that the particle was moving with some momentum earlier in region 1, then it enters region 2, it slows down, the momentum reduces, right? The momentum reduces, right? And so in that case the particle slows down, and again once it reaches the other third region it accelerates to the value which was initially in the region 1. Now somebody would argue that okay, in this case the acceleration is infinite, because it's instantaneously happening here, but it's not the case with the real potentials. Okay, there will be a slow increase and decrease in the like there will be a gradual increase in or decrease in potential momentum. All right, so you need not worry about it. That's why it is how it can accelerate so fast. Okay, so it's not like that. So in this case we have p1 p2. All right, is greater p, the momentum in region 1 is greater than p2. Now it's clearly observed from the value of k. Okay, value, if you compare the values of k here, we can say that like k1 is k2 is actually sorry, k1 is greater than k2. All right, so which implies that p1 is greater than p2. All right, now from this we can also make one thing that we can say that now the lambdas here, the wavelengths, de Broglie wavelengths are inversely proportional to the momentum. So that this implies that lambda, the wavelength in region 2 will be greater than wavelength in region 1. And from this equation, like momentum equations, we can see that P1 and P3 are equal, which implies lambda 1 and lambda 3 are equal. Okay. So in this case, what will happen is this is what we have here. So lambdas, whatever we are talking about, the lambdas are de Broglie wavelengths. De Broglie wavelengths of the particle. So in this case, now we'll write down the wave functions. Okay, let's write down the finally write down the wave functions. I had already drawn it. Let's and spoken about it, but let's write it down finally. So this is psi1. Now this one will be a e to power I kx plus b minus iota kx, and this is x less than 0. All right. And then we have region 2. Region 2. All right. This is psi 2 equal to C iota k1x plus d minus iota k1x. All right, so this is 0. Now the x lies between 0 and a this case. And region 3, is this is, now in this case, let's say that, okay, we have so we are not using a, we are using a, b, c, d, e we are not using, because e we are already reserved for energy. Okay, now this is x. All right, so this is x greater than a for this region. Now I gave you the argument why we are getting rid of g. All right, in all other case, the psi 1 and psi 2 is everything fine. Okay, there is of course a reflection component in both the cases, because there is a change in potential. In this case, for the region 1, b appears because there is a change of potential from v going to 0 to v naught. And then in the second is psi 2, we have a component d, non-zero component d here, coefficient d here, because there's a reflection part here, because there is a change of potential again. And there is change potential from v naught to v equal to 0. All right, so whenever there is a change, whether it's a positive change or a negative change, like in the potential, it will always have a reflection coefficient. Because this is the inherent nature of a wave. Okay, and we are modeling the particle using the wave. All right, so in waves we have this feature. Okay, so since let's argue about this thing, why we are getting rid of g. So since the particles are incident since the particles are incident from left to right. Now one more thing I would like to tell you, somebody asked a question about quantum fluctuations. Okay, so these are there are many terms which will be associated with quantum. Okay, quantum computers, quantum information, there will be a lot of things coming up, because see, there's endless things. All right, so it need not like, you can of course start like do it for learn it for pleasure. Okay, but it's not required at this time. And this is just the basic things which we are learning. This quantum mechanics which we are learning is very, very, very basic. Okay, and what you'll be learning actually is when we go for masters and higher degrees, and there you'll be like doing real things which are currently in research, uh, which has been done there. All right, so mostly like quantum field, when you learn quantum field theory. All right, so those things will give you a different perspective to things which we have been learning here. So I always tell you this, we are always limited by our own knowledge. Okay, so think about it always, and information is not knowledge, and keep that in mind also. Okay, so just knowing about thing doesn't help, not knowing, just having the information doesn't help anyone. Okay, it's like you can google it. Okay, so information you don't need to ask anyone, just google it and see. If you want knowledge, then you have to go study yourself, or talk to the person who is doing it. All right, so since the particles are incident from left to right, um, and also that and also that there is no change, there is no change in potential. All right, that is, and our objective of this course, and my objective too, is to get you through this exam. That's it. Okay, this whatever we are learning here is limited to what the exam talks about, asks you. All right, so we'll be limited to those topics only. So in this case, the remains that is remains v naught as x tends to infinity. So this continues to be v naught. All right. So there will be no reflected. There will be no reflected. There will be no reflected wave. All right. So this implies that g is equal to 0. So I have written down the argument which I gave you. It's the same argument which you have earlier, but it's counterintuitive because the potential is going down instead of going up. But waves, the wave behavior of the waves is this. All right. Now what we have is finally that psi 3 is equal to f e to power I kx. Okay, x greater than a. Now we have to find out now the everything like it's the same process, everything is same. We have the wave function in each case. We need to find out what what are the reflection and transmission coefficients. That's it. This is the same problem again. But what do we need for that? We need the probability current densities, right? For each for calculating those things. Now to find out the probability current densities, we need the coefficients. So our problem reduces to this part only, that we have to find out. Now we'll be not calculating this. We already are experts in this calculating the coefficients by now. All right. I hope you are too. So we can just directly write it down. Okay. From the same analysis as done previously. So we have, it's like we have connected two potentials. This was the one step potential. This was another step potential. We connect, like if you invert the potential, okay, if you have a potential on the negative side also, and then club them together. So you have a kind of a finite potential. So it's like we have connected two step potentials back to back. Okay. One step potential in the forward direction, which we had, and one reversed. Just take a reflection of that and then club them together. We'll have a finite potential barrier. Okay. So it's like that. Just I'm talking about it in a pictorial sense. Okay. So we have to find out B, C, D, and F in terms of A. All right. And reflection coefficients. Let's write down the reflection coefficient. Reflection coefficient. And as you go on studying higher and higher advanced theories, you realize that what you have studied previously, it's trivial, it's useless right now. Okay, so you get a different perspective to look at things. So keep that in mind always, that this is not the ultimate thing you're learning. Okay, so now we how can we write about, what can we write about JR? Now we are talking about reflection coefficient. Okay, so reflection coefficient will be what in the region 1. Okay, so we have the B part and the A part. All right, so in this case we had the momentum, which is in negative direction, and divided by mass, which gives you the velocity, and then you have the number of particles per unit per unit length. Okay, which is the B mod square. Okay, the coefficient of the probability amplitude square of that part, and divided by the incident part. Now the incident will be what? Now this case, uh, what is the incident coefficient here? H
Plus k by
plus
m
H
mod
plus
square.
k by m. Now in this case, we have this one will be okay.
Mod.
So I think there won't be a minus sign here. Is there some problem? So j mod square. Okay, so there's a mod here also, right? There's a mod outside also. The j is this one. Okay, the j is this. This is j. Now there's a mod outside, so this is the mod here. Okay, so if you take this mod, now we'll have the magnitudes here. So we'll finally have this format. Okay, we can write like this. All right. Now the transmission coefficient transmission coefficient. Okay, regarding the syllabus, some of you were asking on my WhatsApp. See, whenever you have doubts, you can ask in the class itself. All right, you can discuss about it. So regarding syllabus, which we are doing here right now, it's now that it's a common syllabus. Whatever I'm doing till now, it's a common syllabus between all the exams, like CSIR-NET, GATE, and JAM. And what uh, what after we complete the JAM part, which is common to JAM. Okay, but now I'll also be doing some parts which are not in JAM but in other entrance exams, as the like just TFR and NetGate, as well as in the PhD entrance exams. Okay, so those are only preparing for only JAM. Okay, you need not attend that. All right, but if you are also appearing for just and TIFR at the MSc entrance level, you should appear for that, or you should attend that class also. Okay, so similarly we can write about the transmission coefficient. Now transmission coefficient will not depend on the C and D part. Okay, because we are talking about the transmission through the barrier. Okay, the particle is going outside, like towards the third region, so we'll be needing the F. All right, F only here, and we don't need the C and D part. Now the transmitted wave here is this, right? If you since we have just wrote it directly, now we can write down to conclude this, that transmitted wave here is represented by this thing, psi3. All right, which is F e to power I kx. All right, and I'll try and finish as soon as possible. Okay, we'll take 1.5 hours of classes. I thought of 2 hours, but 2 hours becomes sometimes hectic for everyone to focus on the screen for so long. All right, so it's better we can like keep it consistent, but we do it regularly. So this is h cross k pi m. So this is jt. All right, this is what we have used here to write down. Now we have just directly wrote down the this transmission coefficient. Now transmission coefficient has other names. You should remember that. Don't get confused during the exams if they give you some other name, which I've already mentioned to you. The transmittance and transmission probability. Okay, these all may have the same thing, the same meaning. Now we need to find out the problem is we need the coefficients which we require here is B and F. All right, so we need to find out B and F. B and F in terms of B and F in terms of A. And also regarding my preparation, I was telling you, like I hope you had a good session, like good interaction with the IITians, which we had invited, and you have learned a lot from them. Okay, how to handle stress and how to like do well in exams. All right, how to prepare for it. So I hope it. I think it was a very fruitful discussion, and I would also spend time in between the lectures to discuss about how to like do well, like score better. Okay, so we just go to the boundary conditions. Okay, for getting the coefficients. Now in this region, what is psi1 and psi2? This is x equal to 0. Now we at this x equal to 0, there are two wave functions which are coming together and two parts of the wave function. Now these should be continuous. Okay, so the wave function should be continuous over the whole region. So we want this to happen. Now this will give us a plus b is equal to c plus d. If you put 0 in both the wave function case, we'll get this, right? X equal to 0. Now the other one which we have here is, now we have, for each situation we have two sets of boundary condition. One is at x equal to a, and the other is at x equal to 0. So we have this thing psi3 x equal to a. Okay, so this will also be continuous. Now in this case we have iota k1 a plus d minus iota k1 a is equal to f iota k. All right, so this is what we have from this boundary condition. Now the next one is the momentum should be the potential here is finite, so the momentum will be continuous there. So we want the first derivatives of the wave function in each region to be continuous at the boundaries. Okay, so this is psi 2. All right, and one more thing, you shouldn't worry about the syllabus. Okay, we have been teaching the course for a long time, so we know how when will the syllabus will get finished. Okay, and you don't not need to worry about it, because people are most worried about when the syllabus covered completely. Don't wait for that. Okay, uh, because what we'll be teaching you is what is exactly required for your exam. Okay, there might be cases like 5 or 10% of the time which will be extra asked in your exam paper, so nobody can guess that. But what we are doing is it will cover most of the more than 90-95%, maybe in some cases 100% also. Okay, maybe for exams like jam. So what you need to focus on really is in your own preparation. Okay, what you have covered till now, what you remember till now. It doesn't matter how much you have attended classes or anything like that. Okay, it doesn't matter. So if you apply this derivative and put x equal to a, this is ik1 c ik1. So instead of getting worried about when the syllabus will be covered and when will be CSIR-NET covered and when will be JAM covered, don't worry about it. This whole course is designed in such a way that it will cover most of the exams. Okay, so what we have, because see what happens is if I ask you question from the previous whatever lectures I have covered, I'll ask you some question, you will not be able to answer that properly. So what's the use of doing so many lectures and not able to solve a single problem? Okay, so I want that everyone should keep revising whatever lectures we are doing. All right, now this is what we get for this thing, the derivative. All right, this is how we just take the derivative and just put x equal to a in on both sides, so you'll get this format. All right, so I think this is correct. Yeah. Now, the transmission, now will it's a very lengthy derivation, we'll not get into that, and nobody will ask you in the question also, paper also. um, Interview also there, it's a rare rarity. All right, so we'll just jump to this conclusion. What does the transmission coefficient look like? Transmission coefficient. Now if you want to see the derivation and do the derivation, in fact it's we are already almost there. We just need to get solve these equations to get f okay, f and b sorry, we need f and b in terms of a, so we have to solve these 4 equations to get that. Okay, so you can do it. It's not a issue, but it's not required at all here. So this transmission coefficient, the transmission coefficient looks like this. Okay, so you can remember the form of this. So this is 1 plus v naught square divided by 4e. Okay, then you have e minus v naught. All right, and here it is sine square k1a. All right, now this is the form you should keep in mind at least till the exam is over, because sometimes they want you to remember the form. All right, so you have a sine square term here, you have this ratio here, and all right, so this is the transmission coefficient. When you completely solve the problem, you get this, and here k1 is here k1 is equal to 2m e minus v naught by h cut square. All right, now the part is loud. Let's discuss what this implies. What are the conclusions we can get from this? Okay, now this one conclusion is like few of the conclusions are as follows. Conclusion. Okay, so if you want to look as a textbook on this. You can look at any of the books which I have recommended. All right. And after we are done with the theory, you should actually look at problems from HC Verma when you're a beginner. Okay. Look at problems from step potential in HC Verma and solve them, the unsolved and the solved ones. Okay. Answers are also given there. And you can also, after that, yeah, so if you're done solving that for net and get, even use a jetily. Okay, the solved examples. uh, if you have time, you can go for unsolved also. And you can also use Griffiths. Okay, but Griffiths problems are sometimes long questions. Okay, so you have to be careful in choosing the questions. Okay, and that is where the student make a miss. Like they are not able to judge which questions are to solve, which to not, which questions not to solve. Okay, so this one, if I want the transmission to be one, let's say I want the transmission should be complete. Okay, it should be one. So what does it imply? Like how can I get t equal to one? Okay, if I want t equal to one, I want this term to be zero. If this term becomes zero, this v naught square sine square term, this becomes zero. So how will it become zero? Now v naught, if we cannot put e equal to v naught. Okay, now this will make this term infinite, and then the transmission coefficient will become zero. Okay, we want it to be one. So for that, what we can do is, now if we see that if we put sine square k1 term a, this is to be zero, what we'll get is, now then we'll get t equal to one. Okay, in that case. So what is that? Let's see. Now k1 a, now this will mathematically, now it's not related to what we have done earlier, 1D potential and all. This is just the mathematics which we are doing here. We are trying to get what are the solutions, like what are the values for required to get the transmission coefficient one. Okay, so how is a the width of the potential and k related? Okay, so this is how we get the n here. So in this case, this is 1 2 3. Okay, now a is equal to n pi by k1. All right, this is n pi h cut n pi h cut divided by h cross k1. Yeah, and my strategy is always like this. When I discuss some topics and give you some example problems, I do not solve all the problems given in previous year in the same topic in the same day. I give you time to go through the theory once again, because it's not always that you'll be able to get everything in one lecture. Okay, you should repeat it yourself, and then that's why I keep on doing revision problems. Okay, even after like 1 week or 2 weeks. Okay, so that is how you recall the concepts. Now in this case, we can write like this: h by 2 pi 2. Okay, so in this case, now if I put k1, what is happening here is k1, instead of this one, let's I have multiplied h and h. Okay, in this case, in n by p. Now from this we got n pi by k1. Now let's multiply this thing, that h and h cross and h cross. Okay, now in this case, what will happen is the pi gets cancelled here. Now we have h by 2, and in this case we have p 2. This is the momentum in the region 2. So we get this result. Now this implies is like this is equal to what? Now let's say that this is n by 2. Okay, now we have h by p2. We have h by p2. Okay, now what we can further write is n by 2 lambda 2. All right, so what we can see a relationship between the width and the de Broglie wavelength for this for the transmission coefficient to become 1. All right, now we have p2 is equal to h cross k1. Now this is the momentum of the particle in region 2, particle in region 2. And similarly, like we have lambda 2, which is h by p2 equal to, this is the de Broglie wavelength, de Broglie wavelength in region 2. All right, now uh, now situation, okay, this situation where the energy is greater than V naught, and we have this thing coming up, this result. Now we can see this. Now this is the example I'm giving you. Okay, you can check this up. I'll not be discussing it here because it will require another lecture or so. Okay, so if you are interested, I would not suggest you to go to that to learn about it. Okay, it might consume some time, but if you are interested, you can look up this effect. Okay, so this theory proves this observation. So this is called Ramsar Townsend effect. Okay, so this is an example. Okay, for observing this calculations what we have done here, that the width of the potential, if it is equal to half integer multiple of the wave de Broglie wave in that region, okay, of the particle, then the transmission will be complete. Okay, so for example is this, you can look it up yourself. Okay, I won't be discussing this now. Let me write down this whatever I told you in statement, that if the potential if the potential barrier region, all right, contains an integral multiple of half de Broglie wavelengths wavelength, all right, then barrier transmission is complete. Barrier transmission is complete, which is t equal to 1. Okay, so that is t is equal to 1. All right, so this is the conclusion which we have in this case. Now how does the t look like? Okay, let's talk about it. How, if we plot the t, how does it look like for the complete t, not this, because this is t equal to 1, which we had discussed. Now let's see how does the t look like if I try to plot it. Okay, now in this case, so this is the value which you have for t equal to 1. This is the t equal to 1 line. This is say 1. Okay, now let's divide this thing into few parts. Now this might not be to scale. Okay, so don't need to worry about it. This is 0.2, say this is 0.4, 0.6, 0.8. Okay, okay, let's make it a little appropriate. Okay, now let's divide it into 4 parts. Yeah, now this makes sense. This is 0.2, this is 0.4, this is 0.6. All right, so this is the t which is increasing in this direction. This is what we are measuring is e, we're showing is e by v naught. Now in this case, let's divide this again into a few parts. Okay, so these are the 2, 4, 6, 8. Okay, so we don't need to worry about the values. Uh, it might not be accurately plotted here, but just see how the curve looks like. So what we have here is the curve will look like this. So let's draw the boundary, the one of the boundaries here, the bounding envelope. Okay, and the curve goes like this. It increases first to 0. This goes to 1 and then comes back and keeps on oscillating like this. Okay, the values keep on oscillating like this, and this envelope which we have drawn here is actually this plot. This is 1 plus 1 by 4e by v naught, and this is e by v naught minus 1. All right, so this is the envelope. If you have if you know how to plot the sine functions in different cases, you will see that there is always an envelope which is there for the sine equal to 1 value. Okay, not sine, yeah, whatever sine theta equal to 1 you have, okay, you have always have envelope bounding the graph. So this is envelope in this case. If you put sine part equal to 1, you'll get this envelope. Now this oscillates between these two values, between 1 and this value. All right. Okay, so this is a graph which you should keep in mind because there are theoretical questions being asked in some of the exams. All right, so we can, let's analyze this plot. So it says that the t oscillates for e greater than v naught. Okay, the t is not a constant quantity. It's not varying like monotonically. Its score keeps on changing. Okay, now if e is greater than v naught, very greater than v naught. Now this also gives us a value which is t tends to 1. Okay, if you keep e to be very greater than v naught, this also implies that the transmission goes to 1. Okay, that is intuitive also. Okay, if you have the energy of the particle is too high compared to the barrier, now the barrier does not affect the motion of the particle then in that case. Okay, because it's too weak to affect the barrier, affect the particle motion. Okay, so the potential the potential here potential barrier is too weak, okay, to affect. And I'll suggest you whoever is also um, like studying from different coaching centers and all, so please make sure that you keep on studying. Okay, don't wait for the syllabus to get over. Okay, it never gets over on time. So keep studying whenever you find time. There's no other options for that. And also some people were saying they were not able to memorize things. The memorization is important, not in the way that you don't understand it and you rote learn it, but in the way that you understand it and memorize it. Okay, memorization is important. If you don't remember the terms, the words and the equations and the formulas, so how will you understand how will you keep this the understanding in mind without the whole building block? Okay, so memorization is important, and there is not like there are, okay, there are people who are able to remember it one they see it, but I also don't remember very often, but maybe I can remember some things. But you have to keep on revising. The revision is only key, revising and recalling. Okay, that is how you build a good memory. Okay. And you cannot give an excuse that you don't remember, you forget. So everybody forgets. All right, so keep that in mind. So the potential barrier is too weak to affect the motion of the incident particles of the incident particles. So we'll finish this part hopefully today itself, so that we can move on to new topic. Now in this case, we now this is always true here in all the cases which we have done. R plus t is 1. Okay, we have not written down r. We can just put t here. We can get r. Okay, you can solve for r that time, but that is not required to remember. Now let's see how the plot looks like in terms of the wave, de Broglie wave. Okay, so let's,
Sir,
yes, 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 go ahead. Tell me.
is
Your voice is breaking.
is
Hello. Your voice is breaking. So this is X, and we have this potential out here. Okay, and this is the, say, the energy level. This is energy level. Now this is Vx. All right. Now what is happening here is, if you have the wave like this, waveform of the wave, de Broglie wave like this, now we can see that the wavelength in region 2, it changes, like it will change and it will increase. The wavelength will increase. It will be more than what is there here. It is, okay. Let's try it like this. So the wavelength increases here. Okay, and then again it becomes the same as the previous one. Okay. All right. So in this case, now this is region 1. Okay, and region 2, this is region 3. Okay, so the wavelength increases in region 2. All right. Now this might not be to scale, just to give you a idea of how does it look if you try to draw the real part of the wave. Okay. uh, so in this case, lambda, now lambda 2 is, you can write it here, let's write it below. So in this case, what we have is lambda 1 is equal to lambda 3, which we have already discussed. Okay, and what we have is lambda 2 is greater than both lambda 1 and lambda 3. Okay, now the amplitude of de Broglie wave, amplitude 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 of de Broglie wavelength will be more in region 2 compared to compared to region 1 and 3. All right.
एम्पलीट्यूड तो सेम होगा ना?
एम्पलीट्यूड आप चेक कर लो, एम्पलीट्यूड आप चेक करना होगा इसमें. एम्पलीट्यूड हमने कैलकुलेट किया नहीं है इसमें. So if we calculate the amplitude and see what are the amplitude here. So in first part there's a is the amplitude, and we have to see the connection between a and c. Okay, so I have not written it down here. So you can look it up and see what are the amplitudes in both the cases. How is c related to a? We didn't derive it here. Okay, so if you see the relation between c and a, there you can find out whether those both are equal or not. All right. Now let's talk about case 2. Case 2. So I hope you understand how to look whether the amplitudes will be same or not. Just see what are the, so I've not derived it completely and I cannot recall that right now. Okay. So if you want, you can just look it up in any of the books I have mentioned earlier. And the c, if you want both the amplitudes to be same, the values like c should be like, whenever we have an equation relating c and a, like c and a should come out to be equal. All right, then only you can say that both the amplitudes will be same. All right, I was more concerned about the wavelength part, which what is the comparison between the wavelengths. Right. So in this case, now we might revisit these topics for the net and gate case in more detail, because I'm restricting myself to the common parts. Okay, so it's not that I'll be leaving anything out, because if somebody is preparing for the MSc entrance exams, they don't require so much information or knowledge. All right. But for the gate and net part, I'll be doing it like whatever the topics, if any topic I've covered already and I've not talked about it in detail, I'll talk about it in later in future lectures. All right. So just one request to everyone, that you keep focus on your exam. That's it. Like what you have been preparing. Don't worry about what is happening. Like everything, like if you're learning from me, I'll complete the part. Okay. So don't worry about it. So this is now this is the energy here, and this is the kinetic energy here. We cannot talk about the kinetic energy in the forbidden region. Okay. Now what we have here is this is say 1, this is 2, this is 3. All right. So what we have here is Vx is equal to 0, which is x less than 0, and we have V naught. Then we have x lying between 0 and a. So this is x equal to 0 and x equal to a. The same potential which we had discussed earlier. Okay, just to remind you of what it looks like. Now this part is x greater than a. Now we'll do the same analysis here. Now let's see. We'll just write down these parts. So region 1. Okay, so we have psi 1 is equal to a I kx plus b e to power minus I kx. All right. Now this is x less than 0, and we have k is equal to root 2me by h cut square. All right. And region 2 is psi 2 c e to power gamma x plus d e to power minus gamma x. All right. Now in this case, we have this is 0. The region is between 0 and a, and gamma is equal to root over 2m v naught minus e by h cut square. All right, so this is the same as the case we had discussed earlier in step potential. This region, the region 2. See, region 1 and region 3 will be same as the previous case. Thus the change here is in the region 2, the classically forbidden region. Okay. Now region 3, all right, which is psi 3 is equal to f e to power iota kx. Okay, so x greater than a and k, and whenever you have any query regarding the course, you can ask in the class. Okay, you don't need to separately contact me for that. Now we have this situation. Okay, everything is fine. We already know the logics behind this type of wave functions. Okay, so we won't get into again, and we need to find out. So in this case, we need to find out, find or calculate. Okay, calculate b and f in terms of a. Okay, so we need the boundary conditions. So boundary conditions, let's see how does it look. See, you can do the derivation, the complete derivation once, and then leave it. Okay, you don't need to, just remember the conclusions. Okay, so psi 1 is equal to the boundary condition is at x equal to 0. Now the wave function will be continuous at the boundaries. This is x equal to 0. This will give you a plus b is equal to c plus d. So let's say this is equation 1. Okay, now we have psi 2 is equal to x equal to a and psi 3 at x equal to a. So this gives you c e to power gamma a plus d e to power minus gamma a e to power minus gamma a. Okay, and this is equal to f e to power sorry, not minus, this will be iota k, this iota ka. Okay, so this is say the second equation. All right, now next ones. Now it's not required for us to label them. Okay, let's not label them. We are not solving them completely. The other boundary conditions which we have here is psi 1 derivative will be continuous here. Okay, now psi 2 by dx x equal to 0. Now if you substitute, like do the derivatives, and we'll get this thing iota k a minus b is equal to gamma c minus d. All right, let's not write it. Okay, I think I'll be okay. If I use it, I'll write down this thing, the numbers. So is psi. Now what we have here is psi 2, okay, at x equal to a, and psi 3 derivative with psi 3 with respect to x at x equal to a. This gives you gamma c e to power gamma a minus d e to power minus gamma a. All right, this is equal to iota k e to power, sorry, this is f e to power iota k. All right, now transmission coefficient. Okay, now we are not deriving it any further than this. Now what we get is important. Now always remember this thing, that we can see that in the earlier transmission coefficient which we had derived, we had seen that there was a sine term, okay, and which was related to the wave number in the for in the within the potential. Okay, wave number which was given by the region 2. All right, so in this case also, uh, what can we have, what kind of what can we have instead of sine? The form is same as the previous one, just that this part where we had sine square term, sine square k1 a, instead of that we'll have sine hyperbolic. Okay, so v naught minus e. All right, so sine hyperbolic sinh square gamma a. This is the change in this part, where gamma is equal to root over 2m e v naught minus e by h cut square. All right, now so you can just remember this, that if you remember one of the forms, and you can just follow, you can just recall this other one, because both have the same form, and just that you have to replace the sine part with the sine hyperbolic part, and and inside it we just have to put the width is already there, and we need to worry about this thing, the k1, whether to put k1 or whether to put gamma. Okay, so this is for the second case, e less than v naught. Okay, so where we have the sine hyperbolic term, because sine hyperbolic terms we know that the wave function has e to power gamma and e to power minus gamma. So the obvious, either it will be a sine function, a sine hyperbolic, or a cos hyperbolic, and we can just now this comes out to be sine hyperbolic. All right, so this is how we can remember the coefficients in each case. Now all these things brings us to the important part, the phenomena of quantum tunneling. Okay, we have already looked into this part, what is the quantum tunneling, but we'll just simplify a few things and get a good looking value for t. Okay, not this one. Okay, this also looks good, beautiful, but that is more small and easy to remember. So what we'll do is quantum mechanical tunneling. Quantum mechanical tunneling. Okay, and in lectures, okay, some of the parts might be clear as like right now, but keep revising it, keep repeating it unless you get the hold of, like, get the hang of it. Okay, so let's the quantum mechanics now. It is a phenomena. It is a phenomena of transmission. It is a phenomenon of transmission of a particle of a particle, all right, through a potential, through a potential of finite width, of finite width and height, all right, when its total energy, its total energy is less than, is less than, okay, less than the barrier height, is less than the barrier height. Okay, so what we have here is b naught as the barrier height, b naught is the barrier height, and a is barrier width. Now the notations could be changed. Instead of a, it could be l. Okay, so you have to just see the definition which has been given in the question paper. Now, what if, now let's do some approximation. What if v naught and a are very large, are very large? What if the potential is very large, and what if the barrier width is very large? Are very large. All right, so in that case, gamma a will be large. Gamma a will be large. All right, so gamma a greater than, very greater than 1. Okay, so what can we say about the transmission coefficient? We are trying to calculate what the transmission coefficient will look like in this case. So sine hyperbolic gamma a, now this is the term which will be affected by this. So if you write down exponential gamma a minus exponential minus gamma a divided by 2. All right, so for gamma a very large, what will happen? For gamma a very large, this term will be very high compared to this term. Okay, this will reduce to 0, this will be very high. So we can write gamma a minus this gamma exponential gamma a. All right, this will be approximately equal to e to power gamma a. All right, and if you write down this finally, what the form of the sine hyperbolic will be for this approximation, this will be approximately equal to So in this case, you can write, in this case, this term becomes this, and the sine hyperbolic term reduces to e to power gamma. Now this is what it is dependent on when we have the gamma to be very high. Okay, and similarly we can have sine hyperbolic square, sine hyperbolic square, okay, which is gamma a. And if you write down this, so this will be e to power gamma a by 2 whole square. Okay, now this will give us e to power 2 gamma a by 4. All right, so this is the approximation we are doing, and let's substitute this thing in the formula for transmission coefficient. So what will we get? So the transmission coefficient is like this: v naught square divided by 4e, okay, 4e v naught, 4e v naught minus e. All right, now this is sine hyperbolic square gamma a. Okay, now what we have here is what we have here is 1 plus v naught square divided by 4e, okay, v naught minus e. Okay, instead of the sine hyperbolic we can write like this: 2 gamma a divide, no, the division is in by 4. Okay, if we just modify this, if we just modify this, so like not modify or simplify this, so we'll get this thing, 16. Now this term, because the gamma is very high, like gamma is very high, a is very high, this term is very high compared to this one. Okay, so we can approximate this to this thing. Okay, so this is e, sorry, v naught minus e. All right, e to power gamma 2 gamma a. And one more thing about the similarity of this problem, similarity of the formula for t in both cases. In this case, there's a v naught minus e, and if you look at the t here, if you look at the t in the previous case, okay, now in this case, e minus v naught is there. So these are the two things which change here in both the cases. Okay, this sign changes to sine hyperbolic, and this also changes. So here in this case, where the energy was greater than v naught, it's e minus v naught, and in this case, okay, and in this case it's v naught minus e. All right, so you can like remember this, like these two things, remembering only one form, so you get this result. All right, now if you just go further, now you can just, now you don't need to write down approximation. This will be equal to 16e, okay, 16e v naught minus e. All right, divided by v naught e to power minus 2 gamma a. Now we can have situations, where for some
V naught square.
cases, sorry, there is v
V
naught
naught
square.
square.
Yeah, v naught square, you're right. So in some cases, the value of, v naught, all right, and e can be chosen such that, can be chosen such that can be chosen such that 16 e v naught minus e divided by v naught square is equal to 1. Okay, all right, so it could be possible. Okay, you can, if you select, say, you can select energy of the potential, like the energy of the particle is e, and you can select v naught to be 10e. Okay, if you solve for that, you'll get it's very close to 1. Okay, it could be that possible. Now let's see the example. Now let's example is say the V naught is given to be 10 E, 10 times of that E. All right, it's a huge potential compared to the energy of the particle. So in that case, if you calculate this, if you calculate this value, is 10 E minus E divided by 100 E square. So this will be approximately 1.44. Okay, so you can see this, and so this approximation is looks good. Okay, for our situation. So what we can do is now finally what we have is now this we can write the T gamma sorry T is approximately equal to e to power minus 2 gamma A. Okay, so this is a cute looking expression which we have here. Okay, from all this hard work we did, this is what you remember for this thing when you are given. Now in this case you have to remember when you can apply this thing. You can apply when a gamma A is given to be very greater than 1. Okay, only then you can apply this. And gamma is, you know, that this is 2me, this is 2me, sorry, not e, 2m v naught minus e by h cut square. All right, so this is the thing you want to take back home. All right, now let's do a problem, or do we have a time? Okay, let's do a problem here. uh, Now let me write down the problem and then we'll solve it. Okay, so this question is was given to you in JAM, but this is relevant to all exams. So a free particle of energy E, a free particle of energy, a free particle of energy E collides with a one-dimensional square potential, with a one-dimensional square potential. Square potential. All right. Now barrier, potential barrier of height v v and width w. Okay, width w. All right. Which one of the following? Which one of the following? Which one of the following statements is R? Okay, there's a bracket here. Is R correct? All right. So the options are this A is for E less greater than V naught, greater than V. Okay, the transmission coefficient, the transmission coefficient, transmission coefficient. All right, for the particle, for the particle across the barrier, across the barrier, across the barrier will be unity, will be unity. Option B, option B gives you for E less than V naught. Okay, the transmission coefficient the transmission coefficient all right changes more rapidly changes more rapidly with with width w than with v. All right, now the c option is for e less than v. All right, if v is if v is doubled if v is doubled, the transmission coefficient is also will be doubled. The transmission coefficient transmission coefficient will also be doubled will also be doubled. All right, now option D is sum of the reflection and and transmission coefficient is always one. Coefficients is always one. So all right, so this is the question given to you, and this is for from JAM 2016. All right, so it could be MSQ also, more than one correct. All right, so tell me what will be the answer, or do you want to think over it in as a homework?
Homework.
All right, so let's take it as a homework, and I'll discuss this problem in the tomorrow's class. All right, and you need not worry about it. I'll be taking the classes regularly as far as I can. Like I'll try to be like every day, because finishing the syllabus is my utmost priority. And I had some problems which caused me to take a very big decision that time, which I posted on the group. But then I will somehow manage to get the things postponed. All right, and let's write down another question for homework. So for a certain particle, so see, if you are able to get the theory and apply yourself to get this solution, this question answer, you'll get a very good satisfaction and you'll learn things. So it's better to look at the solution after you try it. So for a certain particle encountering a barrier, encountering a barrier. All right, the tunneling probability, the tunneling, the tunneling probability is approximately e to power minus 10. Okay, if the mass is halved, if the mass of the particle is halved, and okay, let me write down this halved neatly. So this is halved, and the width and the width of the barrier of the barrier like the barrier which is a rectangular here. We are talking about a rectangular barrier. Rectangular. All right. Barrier is doubled. Okay. The mass is halved. The barrier width is doubled. Approximate value of transmission tunneling probability. Approximate value of tunneling probability. Now, in this case, the word tunneling probability has been used. Now, this is same as the transmission probability. Okay, this is the same as the transmission coefficient or transmission probability. So there is another word you are learning here, which is tunneling probability. Tunneling probability is the same as the transmission probability. Okay, so tunneling probability. All right, so is so let me give you the options. Options are A, e to power minus 10 by root 2, and B. Now, when somebody talks about this tunneling thing, now if they are not talking about transmission, now you should automatically assume the approximation which we have done in quantum tunneling, uh, okay, topic. So you don't have to worry about the transmission coefficient which we have derived, not derived, in fact, wrote it down directly. So in this case, so this is a question from some, I don't know which exam. I don't remember the exam, but it is from, I think, some net exam only, not from physics. Okay, maybe from chemistry, but it's good for the basics. All right, so let's sign off here if there are no questions.
Hello, sir.
Yes.
So in the case one, why there is a fluctuation of the T?
No, that is what we
Transmission.
are getting the equation, right? Why we have to like, this is what we are getting from the mathematics which we have. That is why I gave you example here. I give you example of this phenomena. What was that? The Ramsar Townsend effect. You can look it up as an example. All right. So this is what we are getting from the. This is a mathematical. You can see that there's a mathematical aspect of it. Okay. So if you want to look at from the physical perspective, you can look it up this example. Okay. If I talk about it, I have to discuss it for maybe one lecture or two lectures. So it will just waste our time, nothing else. Okay. So if you want to look it up, you can just Google it. You'll get this thing. Okay.
Okay, sir.
Yeah. All right. If there are no other questions, then we can sign off and just take this as a homework, and we'll discuss it in the next class. Now, the second question is straight, very, both the questions are not very difficult. All right. Thank you for watching. Have a great day.
Thank you, sir.
All right.